Hey guys, my name is Zach Lassiter, and I'll be discussing a lab I did about the motion of a spring mass system in which the mass swings in an arc while oscillating on a spring. The point of this lab was to predict the motion of the spring mass system in Tracker in order to extract position values for each time step. I then created a computational model in VIDLE using fundamental principles such as Newton's second law and the energy principle. I then compared both models, and the results were that the predicted motion of the mass followed closely to the same motion as the data received from Tracker. They slightly differed, but this was mainly due to the fact that the time step in Tracker was 20 times larger than the time step in the computational model. And after doing the computational model, it was concluded that the spring mass system does satisfy the energy principle. Here we have two fundamental principles that are used in this lab. The first one is Newton's second law, and this one was just used to update the velocity of the spring in order to calculate the change in energy as time went on. And here's the energy principle equation, and that's equal to the change in energy is equal to the change in kinetic energy plus the change in potential energy of the spring plus the change in potential energy of gravity. Both these are used in the computational model. Here we have the equations for kinetic energy, which is equal to 1/2 mv squared. The equation for potential energy of gravity, which is equal to mass times gravity times height, and the potential energy of spring, which is equal to 1/2 times k sub s times big S squared. Here we have to calculate k sub s in the equation. Period is equal to 2 pi times square root of mass divided by k sub s. The period was calculated by taking the time it takes to do one full period, which is equal to one wave, and that was equal to 1.52 seconds. We then solved for k sub s and got 6.87 newtons meters. We then used the equation mg equals k sub s times s to get the value of s, which was equal to 0.573 meters, and s is equal to L minus L naught. So we solved for L naught, and we got that as a value of 0.27 meters. 0.127 meters. Here we have Dr. Greco holding a mass connected to a spring. The relaxed length of this system is equal to 0.7 meters. When you run it, you notice that the mass system is going in an oscillating manner as time goes on. And as the time went on, it was recording position values for the x and y. These x and y's were copied over to an Excel and saved as a CSV file. Here we have the mass of the ball in the code as 0.402 kilograms. Everything mentioned right here is everything that was just mentioned in the PowerPoint, but this while loop is where it all happens. Here we calculate for the gravitational force, the spring force, and the net force, as well as we use Newton's second law to predict the final velocity, or the updated velocity at different time steps, as well as the position. We then update the spring with different positions in order to calculate the change in kinetic energy at different points, as well as the change in potential energy of gravity, potential energy of gravity and the potential energy of a spring. And we're going to run this. Okay. You can see that the red ball is lagging behind a little, and this is mainly due to the fact of the time step being 20 times larger in Tracker than it was in the computational model. Another factor that affected it was the fact that drag force was catching up with the spring because we didn't account for that. And there's also some slight round-off error. And that accounts for all of the discrepancy between these graphs right here and why they're not all uniform. The red graph right here represents the change in potential energy of the spring. The green one is potential energy of the potential energy of the Earth, the change in it. And then the blue one is the change in kinetic energy, and the yellow one is the total energy. And as you can see, it's really close to zero, which is really good. So for our thing, what does it mean? For your model system, is the energy principle satisfied? The work done by the surroundings is equal to the change in energy, but because there's nothing in the surroundings with the Earth, spring, or mass being in the system, then the work and by extent the change in energy should be zero. There is no outside work done to this system, so W is equal to the change in energy. And the change in energy of the graph is zero, which confirms that the energy principle is satisfied. But if you zoom in really close, it's not completely equal to zero, and this is mainly due to the fact we didn't account for slight air resistance. So let's head over to the second one. What does it mean? Using the data you obtained in Tracker, make two separate estimates of oscillation, the periods, mainly in the x and y. For the x, it's in a pendulum motion, and the period for a pendulum is 2 pi times the square root of the relaxed length divided by gravity, and this gave me a value of 1.76 seconds. For the y component, the period is equal to 2 pi times the square root of m divided by k, and they gave me a 1.52 seconds. And that makes sense because it should take longer in the x, because as you can see from right here, the x is clearly takes longer to do a full period than the y. And to confirm that, we have these two graphs. This one's the tracker values for x and t, and this one's against y versus t. And just by looking, you can tell that the period to do one full cycle in x is bigger than it's how long it takes to do a full period in the y. That's all I have, though. Thanks for watching.